Welcome everyone to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim R&D Manager and also the Associate Director of the National Center for Simulation and Rehab Research here at Stanford. I'll be serving as the moderator for today's webinar. So I'm pleased to welcome today's presenter, Carmichael Ong, who's a graduate student here at Stanford. He'll be presenting on simulation-based design of devices to enhance a standing long jump. So OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movement of humans and animals. So OpenSim has tools for inverse dynamics, optimization, so you can solve for muscle and joint forces, methods so you can create simulations for motion capture data, and then tools that allow you to analyze and visualize the results of your simulations. So the first goal of this webinar series is to showcase research that's being performed with the OpenSim software platform. The community of users of OpenSim is also growing and increasingly geographically diverse. So the second goal of our webinar series is to provide a platform for this community to communicate with each other and collaborate. Before we get started with Carmichael's presentation, I have a few reminders about the format of the webinar. So we'll address all of your questions at the end of the presentation using WebEx's Q&A panel. And if you need any additional technical help during the webinar, you can consult the guide on our website. So now I'd like to go ahead and introduce our speaker for today. So Carmichael Ong received his BS in Biomedical Engineering from Brown University and holds an MS in Bioengineering from Stanford. He's currently a PhD candidate here at Stanford in our Neuromuscular Biomechanics Lab. Carmichael is the winner of several graduate fellowships, so from the NSF as well as Stanford's BioX program, and he was also recently selected as a Cybel Scholar. So Carmichael is using predictive simulation to better understand and improve human movement, which we'll learn about today. So with that, I'll let you take it away, Carmichael.
Thank you so much for the introduction, Jen, and thank you all for tuning in today. Today, I'm going to share our initial work in using simulation to help design wearable robotic systems. To give a concrete example, I will be focusing on work that we have done to use simulation to design devices to augment performance of a standing long jump. Wearable robotic devices offer great opportunity to improve human performance for various movement tasks. The video on the right shows a device from Malcolm and colleagues that decreases metabolic cost of walking by assisting ankle planar flexion torque at a specific point in the gait cycle. The onset timing of this additional torque, however, is later than the onset timing of the normal human walking, which suggests that there are interactions between devices and the human that are not yet elucidated. Furthermore, subject variation can lead to varied performance of these devices. Together, these problems lead to increased time spent in prototyping and testing. Work by Ferris and colleagues studied the human-device interaction during hopping. A spring-loaded exoskeleton seen on the left was designed to reduce metabolic cost of hopping. They found there was a reduction in soleus muscle force, but the work done by the muscle was not reduced. Simulations helped to show that the soleus muscle was operating in a less efficient state. On the force length curve, the spring-loaded exoskeleton case, shown by the SE here, was further away from the optimal length than the no exoskeleton case, shown here. The muscle was also shortening faster, as seen by the force velocity plot on the right, also decreasing the muscle's ability to generate force. We wanted to see if simulation could be used beyond just analyzing experiments and see if we could create a flexible optimization framework that can be used to predict how adding assistive devices will affect performance. In this case, specifically, we looked at increasing performance of a standing long jump. We first developed an optimization framework that synthesized motions that captured many salient features of a normal adult male jumping, validated by comparing the simulation results to previous experiments. We then added simulated, active, and passive assistive devices and investigated whether the framework could help choose device parameters. Our manuscript covering this work has been accepted in IEEE Transactions on Biomedical Engineering. We also tasked students in a class taught at Stanford to design an exosuit that increases jumping performance. The framework allowed them to design exosuits that more than doubled the jump distance achieved before. So why did we choose a standing long jump? Jumping is an important movement in athletics, and as we can see in the video, requires a complicated timing of muscles. Here are two American football athletes performing a standing long jump as a performance test. We first see the counter movement phase over here on the right, where the athlete flexes his lower body joints, followed by an extension phase of the lower body joints and elevation of the shoulders. The athlete then must prepare for landing and must land without falling. Although this is a complicated movement, it is mainly a planar movement, so the salient features can be captured in a simple model, and there is a clear goal: maximize distance while landing without injuring oneself. For these reasons, it is an ideal motion to serve as a proof of concept for simulation-based design. So now we're going to dive deeper into the details. Here's an outline for the remainder of the talk. We'll start by looking at the optimization framework with an emphasis on the model and objective function. We'll also look how we validated this nominal model, and then we will dive into how we modeled and evaluated different types of devices. We'll also review the work of the students, and I'll go over really quickly about how you can access the source code. The first step in developing a predictive framework is to create a method that can generate a nominal case of jumping without experimental data. Once we have confidence in the framework to capture salient features of a standing long jump, we can then model devices and use the same framework to predict performance. First, a human model must be chosen and implemented that can capture salient features of a standing long jump. The model contains the rigid bodies that represent the human, as well as any actuators that drive the model forward. We want to choose a model that is complex enough to capture important features of the standing long jump, but is as simple as possible to decrease iteration time of the optimization. The model chosen for this study is based on a model previously developed for standing long jumps by Blake Ashby and Scott Delp. The model is planar and is composed of 6 segments: the foot, the shank, the thigh, a combined pelvis, torso, and head, the upper arm, and the lower arm. There are 7 degrees of freedom, 3 for the location and orientation of the torso, and 4 pin joints at the ankle, knee, hip, and shoulder, whose angles are described by the 4 thetas. The elbow is locked. 4 physiological torque actuators at the ankle, knee, hip, and shoulder drive the model, represented by the 4 T's. These actuators represent the role of muscles. Ligaments at each joint are modeled by rotational springs that engage if the joint hyperflexes or hyperextends. The physiological torques are physiological because they are based on normal adult male strengths and are dependent on position and velocity of the joint, just like muscles. As an example, here's a plot of the maximum flexion torque that the hip can produce plotted against joint angle for 0 joint velocity. The capacity of a human's possible joint torque is also a function of velocity. We can see here that if a person's joint is already flexing, the person's capacity to generate torque decreases. This is modeled by multiplying the original curve by some scale factor, t velocity, that is based on the velocity of the joint. If the joint is extending, however, the capacity of the joint flexion torque actually increases. So we see as joint velocity increases, the capacity for flexion torque decreases. The last term, which stands for activation, the A, represents the effort of the joint torque, and for flexion is represented by a number between 0 and 1. Each of the other joints, the ankle, knee, and shoulder, have their flexion torques described in the same way, but have different T position and T velocity curves. Each of the torque actuators can also create an extension torque and follow the same form, except their activation is represented by a number between -1 and 0. The sign of the activation value controls whether the torque actuation will produce a flexion torque or extension torque. Contact is modeled by 2 point constraints, one each at the heel and toe. Each constraint is released at the instant when the vertical component of the force goes to 0. Returning to our figure, the next step is to add a controller for the actuators in the model. Each of the actuators is controlled by a different control signal that give the value of activation of each actuator as a function of time. These signals are constrained to be piecewise linear functions with control points every 50 milliseconds. These controls are then used in the forward simulation. To optimize the set of controls, we use the dynamics block to feed states into an objective function. The objective function calculates the performance of each forward simulation. Then it passes the output, we pass the output of the objective function into an optimizer, and the optimizer determines the next guess of controls based on previous objective function evaluations. Jump performance is scored by using an objective function that captures 4 high-level task-based physical metrics and 1 term used as a heuristic for the optimizer. We use the activation values of the control signals as the variables of the optimization problem. The first metric is distance. Since we want to minimize the objective function, we use the negative of the jump distance to reward jumps that travel further. The jump distance is scored as the initial position of the toe before takeoff to the position of the heel at landing. We penalize jumps that are not likely to land without falling. We quantify this by ensuring that the location of the center of mass at the time of landing is not too far behind the heel or too low to the ground based on experimental data. The model on the left shows a jump that would not be penalized, but the one on the right would be. We penalize jumps that would lead to injury as well. This is quantified by penalizing excessive use of the ligaments when joints hyperextend or hyperflex. The model on the right is hyperextending its hip joint and would be penalized. We penalize the jump if it was likely to slip during takeoff, since contact is modeled by point constraints. This is done by ensuring that the ratio of the horizontal ground reaction force to vertical ground reaction force is below a threshold. This is most relevant right before takeoff, and the model on the right would likely be penalized as it would probably slip if it were to take off in that configuration. A fifth term was a time penalty. A time penalty was enforced if the total jump time was below a certain threshold. This was used as a heuristic to guide the optimizer away from local minima, where a short hop would be taken. For the optimizer, we use the covariance matrix adaptation optimization method developed by Nicholas Hansen. To briefly describe it, a population, shown by the black dots, is generated from a distribution described by a mean and covariance matrix, represented by the dotted lines. The distribution updates each generation to make the population more likely to sample points closer to minima, as represented by the white area. Since dynamic optimization problems tend to be non-smooth and non-convex, this method is useful as it does not need derivative calculations. If you'd like more information, there are good references both from the author Hansen and the Wikipedia article. To assess the accuracy of the optimized solution, we compare the simulation results to results from the experimental data. This ensures that the optimized solution captures key elements of the standing long jump. We implemented this framework in OpenSim. The video shows the progress of the optimization. At the end of each jump, the jump distance is shown along with the objective function performance value. We can see as the optimization continues that the jump will start to include important features such as the counter movement, followed by extension of the lower limbs and flexion of the upper arms just before takeoff, and preparation for landing. The final optimized jump achieves a jump distance of 2.27 meters. We can more rigorously assess accuracy by comparing this simulation with experimental data. There are various parameters reported about the kinematics of the center of mass at takeoff. The first 3 columns are data from previous studies, and the last column contains results from simulation. We note that in the first row, that jump distance of the simulation is similar to the experimental data. The second and third rows, D and alpha, describe the location of the center of mass in relation to the toe at takeoff. D is the horizontal distance from the toe to the center of mass, and alpha is the takeoff angle. We can see that the location of the center of mass agrees closely with experimental studies. The last 2 rows describe the velocity of the center of mass, where V is the magnitude of the velocity, and theta is the inclination angle of the velocity vector. We can see that the simulation also agrees with the experimental studies. These plots show the joint torques on the y-axis against the time relative to takeoff on the x-axis for the hip, knee, and ankle from top to bottom. In each plot, The gray area represents the average plus or minus 1 standard deviation of experimental data. The solid line represents the joint torques from the simulation. These are plotted until takeoff time. We see that the important features of each joint torque are captured by the simple model. We see that the ankle torque, shown here in the bottom, follows experimental data closely. At the knee, we see that maximal extension torque is close to experimental data, as seen up here, but that the onset of the extension occurs late. This could be due to the fact that the torque actuators do not model the delay between the control signal and torque production that we would expect, since muscles have a delay between excitation and force generation. At the hip, we see a similar trend as with the knee, where the maximum extension torques generated agree with experimental data, but the onset of this extension phase occurs later. These plots show the ground reaction force from experimental data from Ashby 2002, shaded in gray, against the simulation results shown by the solid line. Above, we see the horizontal ground reaction force captures the counter movement phase early, with a relatively small magnitude of force, followed by large forces just before takeoff. Below, we see their vertical ground reaction force. We see a dip starting approximately a half second before takeoff, followed by a large force of several body weights just before takeoff. Although the dip is much lower than experimental data, it still shows that the model captures the counter movement phase followed by large ground reaction forces just before takeoff. Now that we have confidence that the model does capture important parts of a standing long jump, we can use a similar framework to design actuators. Let's go back to the diagram of our framework. Exosuits can be added to the human model. Since the device is now part of the total model, the control inputs can change for both physiological actuators as well as the devices at the same time. In addition, parameters of passive elements of the model can also be changed by the optimizer. We modeled both active and passive assistive devices. We assumed that all devices were massless. We allowed the active device to turn on once to give additional extension torque of up to 100 Newton meters. For each device, this led to 3 parameters that could be optimized: the magnitude of the force, the time when the torque engages, and the duration of the applied torque. The passive device was modeled as a rotational spring, which had 2 adjustable parameters: the stiffness of the spring and the equilibrium position, or the position of the joint when no torque is applied. We tested 5 device configurations in total. 3 of the device designs added a single active device to a lower limb joint at the ankle, knee, or hip. An active multi-joint design added an active device at all 3 of the lower limb joints. The passive multi-joint configuration added a rotational spring at all 3 of the lower limb joints. We optimized each of these configurations using our framework, and the results for the kinematics at takeoff are shown here. In particular, though, here, we note that all configurations led to an increase in jump distance. We'll see this table again and inspect it in more detail for each of the cases. We'll first take a look at all of the cases where a single active device was added to a lower limb joint. The nominal jump serves as a point of reference on top, along with the 3 assisted cases. In each of the assisted cases, a green ball will appear when the device is applying an extension torque. It might be difficult to notice, but try to note the actuators turning on during the extension phase. Note that there were similar jump distances for all of the assisted cases as well. I'll play it a couple more times too here. And one more time. So for instance, for the knee, we'll see a green ball turn on right here during the extension phase. Here are the kinematics at takeoff for the nominal case and single joint active device cases. We see that although the jump distances were similar for each of the assisted cases, there are differences in the kinematics at the time of takeoff. An experimental study inspecting optimal takeoff configuration noted that optimal jumps are achieved with lower takeoff angles, shown by alpha, and higher takeoff velocities, shown by B. We can see a trade-off between these two quantities in a couple of cases. We'll highlight the ankle and knee case. The jump assisted by an ankle device had the highest takeoff velocity V, but the largest takeoff angle alpha. Conversely, the knee device had the lowest takeoff velocity, but the smallest takeoff angle, which led to similar jump distances. Now we'll discuss the multi-joint active device. We'll see the nominal jump alongside the assisted case. For the assisted case, green balls around the lower joint will show when the active devices turn on. And we'll generally see them turn on in the extension phase right there. The torque time plot on the left shows the total torque of the assisted case in black and the torque during the nominal simulation in gray. We see that a similar strategy is taken by the human during the first half of the simulation, during the counter movement phase. So we see that in the hip and the knee and the ankle down here that we have similar torque values. Now we'll add in the individual contributions from the physiological actuators shown in red and the device actuators shown in blue. We see that the device adds extra torque during the extension phase that the physiological actuators cannot provide due to the force-velocity relationship. We can see in the pose at takeoff, shown here, how the actuators help achieve a longer distance. The takeoff angle, alpha, is smaller than the nominal case, and the magnitude of the velocity v is much higher. Finally, we will inspect how the multi-joint passive design helped improve the simulated jump. The nominal jump is on top again, and the assisted jump is on the bottom. During the assisted jump, green balls will again denote device extension torque, and red balls will denote flexion torque. The radii of the balls will also change, and they are proportional to the torque applied. We'll also generally see the large green balls during the extension phase there, showing the large amount of assistance during the extension phase. The torque versus time plot on the left shows the total torque of the assisted simulation in black and the torque during the nominal simulation in gray. Like in the multi-joint active device, we see that the counter movement strategy remains unchanged, as the two curves are similar at the beginning. Inspecting the individual torque contributions from the physiological torques in red and the device torques in blue, we see that the similarity is achieved in a different way. To highlight this, we see in the ankle plot on the bottom that the physiological torques counter the extension torque of the spring to yield a total torque of approximately 0. A similar effect is seen in the knee plot in the middle. Another key point is that the devices have been optimized such that the torque provided by each of the springs is approximately 0 at the instant of takeoff. We can see that by looking at the blue lines that approach 0 at each of these points. This suggests that the optimizer has chosen the spring's equilibrium points such that they can provide extension torque until the instant of takeoff. We can look at the kinematics at takeoff to see how the extra extension torque before takeoff improves jump distance. With the highest magnitude of velocity v and the smallest takeoff angle alpha, this design led to the longest jump of all designs. This framework can also assess if an injury due to hyperextending or hyperflexing a joint may occur during a jump. This is a plot of the ligament torques during all 6 conditions. In particular, we see that the ankle may be at risk in a number of scenarios, especially for the multi-joint active design shown in panel B here, the ankle-only active design, panel D, and the knee-only active design, panel E. There are 2 ways this could be addressed. During the optimization, a penalty on the maximum ligament torque could be added. Also, adding joint stops into the design could also help to decrease injury risk. This covers much of the work laid out in our recently accepted paper. The paper has more detail than we can cover in this presentation, and we encourage you to read the paper for more information. To further test these methods, we gave the framework to 3 students who were tasked with designing a performance-enhancing exosuit over the course of about 3 weeks. 2 of the students designed a similar exosuit, whose schematic is shown above. It has 3 torque motors at the ankle, knee, and hip, represented by the blue circles. Zoomed in, we can also see rotational springs and joint stops located at the ankle, knee, and hip. And these rotational springs are clutched so that they disengage at takeoff. The 3rd student's design, shown below, also used 3 torque motors at the ankle, knee, and hip. He also used 3 linear springs spanning the joint. This video shows the simulated jumps of these designs after optimization was performed. Some key points to note while watching the video is that the counter movement is preserved, and that this is the time during which the passive elements were preloaded using device's torque actuators. The 2 models above also had better performance due to a smaller injury penalty due to the joint stops and the advantage of the clutch springs at takeoff. Finally, it seems that using the human-to-control landing instead of the exosuit was sufficient to meet the landing criteria. The work shown here shows our first steps into showing that simulation can be used to help design exosuits using an optimization framework and principles of human movement. We developed a framework that first synthesized a simulation of a standing long jump that captured salient features. It was also flexible and accessible enough for 3 students to design exosuits that more than doubled the simulated jump distance. Finally, I'll give some details on how to access the code used for these studies. The source code and results are available at the link here at simck.org/home/predictive_SLJ. SLJ means standing long jump. The code's written in C++ and uses the OpenSim API to define the model and perform forward simulations. The code given in the project contains a version of the CMA optimizer seen here, implemented in C, and provides a class for the physiological torque actuators presented here, which is not available in OpenSim. It also has some classes for calculating different terms of the objective function given a final state. The results, also shared at the website, contain the states files and forces files for each of the 6 cases, the nominal case and 5 assisted cases presented in the paper. And this work, I just really want to thank a lot of people. It's a really long list of people that helped out, but specifically, Tim Dorn and Jack Wong gave a lot of help at the beginning, and AJ Seth, Michael Sherman, and Ivan Habib all gave a lot of good technical help. I definitely want to thank the students that really tried out the code and showed that it really could go somewhere. And I want to thank the support of NCSRR, the Mobilize Center, DARPA Warrior Web, and BioX for funding the project and me. So, and thank you all for listening today.
All right. Thank you, Carmichael, for a great talk. Now we can go ahead and get started with our Q&A session. So as I said at the beginning, all of our quick questions will be text-based. So go ahead and find the Q&A box on the bottom of your screen, the bottom right. Type in your question, make sure you select to ask all panelists. So go ahead and type those questions in. While we're waiting for questions to come in from the audience, Carmichael, could you tell us a little bit more about why you selected CMA as the optimization algorithm and how you think it might compare to other routines?
That's a really good question. We find a lot in these types of problems that it's not a smooth objective function, and so there's a lot of local minima, there's a lot of spiky parts of CMA is that it doesn't explicitly use a derivative. So it's less likely to be caught in some of these local minima. Also, it's a stochastic optimizer, and so it kind of chooses its population given a distribution. So it allows it to be more likely to get out of these local minima as well. And we found that that was really useful in solving our problem, and is also been useful in some other frameworks that we've seen, like from Tim Doran and Jack Wong's work with walking and running.
Okay, great, thanks. Let's see, here's a question now from the audience. This is from Jeff Rankin. So he's wondering, how does CMA compare to other non-derivative stochastic type optimizations like particle swarm or simulated annealing? So getting into more details.
Right, that's also a really good question. I'm not super familiar with particle swarm, but I will say that in one way it's almost kind of like simulated. It has similar some similarities to simulated annealing, where it can kind of heat or cool or kind of adjust its search space as it's finding better or worse solutions. And that also is a way that allows itself to get out of these local minima. I will say we didn't specifically test those methods out on this. We kind of went with CMA and it worked. That being said, simulated annealing is a great method, and I believe actually Blake Ashby did use simulated annealing originally with this problem.
All right, and a follow-up question from Jeff is approximately how many iterations did CMA take to optimize?
So there's a couple ways to answer this. So I let it kind of sit around, and it would converge time-wise in probably about an hour, and that would be several thousand generations. But since the model is so simple, it's quite fast. But we did a little bit more work to get it out of some of these initial solutions that it would find. So there's a lot more information about how we did that in the paper, but kind of briefly, because it's stochastic, I actually reran the same initial guess 20 times, and then picked the best one, and then used that as a new seed, and then started another 20 optimizations from there. And I found that worked pretty well, and I've been finding kind of solutions that weren't getting stuck in the local minimum. Time-wise, that took in total a few days using a cluster here at Stanford.
Okay, thanks, Carmichael. If anyone else has other questions, go ahead and type them in. Just says thanks. So I'll ask another question while we wait for other audience questions to see if they come in. So what do you think are the next logical steps with your framework to move forward?
Sure. So there's always, one of the limitations actually here is that the actuators are torque actuators around each of the joints and not individual muscles. And so we can't explicitly answer any questions about individual muscles. So increasing complexity to adding even muscle groups would be helpful to answer questions regarding how these actuators could and their interplay with individual muscles. Also using kind of on a higher view from general dynamic optimization, using this framework to study other movements such as walking and running I think would also be something interesting.
All right, so we have another question. Thanks, Carmichael. We have another question from Jeff. Why did you choose your particular method of ground contact? And then thoughts on how you would model contact for other movements like walking.
That's also a great question. You know, we chose it because it's really fast, and I think for a standing long jump, you'll get most of it without letting your model explicitly slip. you'll get a lot of the counter movement phase and extension phase. That being said, I did try some compliant contact, so using like Hunt-Crossley forces, and that was really that slowed down the forward simulation quite a bit, the integration phase, and didn't really add too much to answering the questions. And concerning contact and other movements, I would definitely probably use compliant contact for something like walking and running. And the positive to that is that it's a lot easier to deal with coming into and out of contact repeatedly, which is needed for walking and running. But in this case, right when the model hit the ground, we would stop the simulation there and assess the performance there.
All right, so if there are no further questions, anyone, I think we can go ahead and wrap up. As Carmichael said, feel free to download his code and send him any other questions that come up in the future. So to wrap up, again, thanks Carmichael for a great talk, and thanks to the audience for the great questions. Let's see, OpenSim and this webinar series are supported by several grants from the NIH, including the NIH grant that funds our National Center for Simulation and Rehab Research. And you can find more information about the center, upcoming events and webinars and other resources on our website at opensim.stanford.edu. And we hope that you'll complete the short survey that will appear in a pop-up window at the conclusion of the webinar. So thank you everyone for participating, and we hope you'll continue to stay involved with OpenSim.